All right, welcome to Fun Fact Friday. In this one, I want to look at a little history of math that's kind of interesting and has a surprising ending. So we're going to look at geometry specifically, all the way back from Euclid in 300 BC to Janos Bolyai, I can't pronounce it correctly, in the early 1800s. And in order to understand kind of this history and what's going on, we need to do a little bit of background first. So first we need to talk about something called mathematical proof. So you often hear of people talking about proving something, especially like in terms of a court case or, in biology, let's say, you could talk about things being proven or not. Even in physics, the law of gravity, we consider that a set fact. Okay, but that's not enough for mathematical proof. Okay, the law of gravity, we test and test and test and test and test and test and say, yes, this seems to work. This matches everything. I believe it's going to work. Mathematical proof, we need to be 100% sure. Not 99.9999% sure, 100% sure. So that means just because gravity works the way we expect here on Earth and what we can observe in the universe, how do we know gravity doesn't work differently somewhere we can't observe? I mean, we assume the universe is, orderly and gravity will work the same, but we can't be 100% sure. So mathematical proof, we need that 100% certainty. So what we do in mathematical proof, okay, we assume certain facts, and then we have set logical rules we can follow, okay? So we follow logical steps, and they're very specific what you're allowed to do in mathematical terms. Using those facts, we can follow these logical steps and get to a new fact. So that's a general idea of mathematical proof. Okay, you have to state what you're assuming, and you can only use certain logical steps to draw new conclusions from those statements. All right, so let's start with Euclid. So Euclid was around 300 BC. He wrote the very first mathematical textbook. The very first textbook was in math, because math is awesome. So he wrote something called the Elements. You can find lots and lots of free translations of it online. It's really fun to work through. The idea then, right, he started this idea of mathematical proof where he stated definitions, common sense notions, and then what he called postulates. He had 5 postulates, and these were his assumptions. These were his starting point. And here's where the history of geometry gets interesting. Euclid's 5th postulate is often called the parallel postulate. And he states it in one way. I'm going to state it in the more common way that we use nowadays. They end up boiling down to the same thing. But the idea is if I have a line, any line, and I take a point not on the line, there is only one parallel line passing through that point. That's the idea of the parallel postulate. Okay, so if you look at his first 4 postulates, they're simpler things. They're more obvious things. So people felt that this postulate was a little intricate for a postulate and felt like it seems like I should be able to prove this as 100% fact based on those other 4 assumptions. So for thousands of years, people would start with those 4 assumptions and prove a new thing, 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 hoping to lead to the parallel postulate. Thousands and thousands of years. Now, remember, when they're doing that, they have to be careful and not use anything that relies on this 5th postulate. So, for example, you're told in high school geometry all the time that the sum of the angles, right, the measures of the angles technically, in a triangle is 180 degrees. You're told that over and over in high school geometry. Well, that is proven from the parallel postulate. So you can't use that fact in what these mathematicians were attempting to do, okay? Because we are trying to show the parallel postulate. We can't use it. All right. So enter into the picture Giovanni Sacchieri. And again, I apologize for my pronunciation of these names. I'm doing my best. Okay. So Sacchieri lived in the late 1600s. So he was born in 1667 through the early 1700s. Okay. At the very end of his life, he published a 2-volume work. So he'd been working on it probably decades to get it that long, all based on trying to prove this parallel postulate. And he proved all sorts of crazy things, like we couldn't use the fact that a triangle has 180 degrees, but from those base postulates and base assumptions, he was able to show that a triangle had up to 180 degrees, just not exactly, okay? So he was also able to show that if a rectangle exists, I know that seems weird. You're thinking, duh, rectangles exist, but you got to understand mathematical logic and rules. If a rectangle exists, then parallel postulate is true. So he spent a lot of his work just trying to show that a rectangle exists without having to use the parallel postulate. Okay, that's what a lot of his work was. And he worked with this shape that's super famous now called a Sacchieri quadrilateral. And the idea of it is the bottom angles are right angles, the sides are congruent, and that's it. That's all we know. So all his work relied on trying to show that these top 2 angles here are right angles. Now, he was able to show they have to be congruent. He was able to show that they can't be obtuse, they have to be right or acute, okay? And he worked forever and ever and ever trying to show that they can't be acute, because if they're not obtuse and they're not acute, they must be right angles. And then he has a rectangle, and then he gets the parallel postulate, according to mathematical logical steps and rules. But he could not show that you could rule out acute, okay? Acute angles. So that seems weird, I know, because you're thinking in normal geometry, but go with me. So then enter the picture, century later, we have Janus Bolyai. Okay, so this is early 1800s to mid 1800s. He also was obsessed with trying to prove this parallel postulate, right? Take those beginning postulates and find results. Well, he eventually, even though his father told him, give up, it's impossible, it's a hole that you never get out of, he eventually did come to the conclusion that it's impossible. You can't prove the parallel postulate. It needs to be assumed because you can't just prove it from the other 4. All right, so he then started playing with the idea of, well, the parallel postulate, let me go back, scroll up, says that there exists exactly 1 line through that point. So he played with the idea of, well, what if there are no lines that are parallel? Or what if there's multiple lines that are parallel? And that led to what are called non-Euclidean geometries. Now, other mathematicians also were playing with this idea at the same time. There's a mathematician called Lobachevsky. Gauss also was probably playing with this stuff at the time, but Bolyai was definitely one of the leading figures in this. So let me show you what we mean by non-Euclidean geometries. It's really cool. So let's say we have a sphere. Let's say this is the Earth, if the Earth was a perfect sphere. And here's the equator, okay? All right. So triangles on the surface of the Earth are not like triangles we're used to in a flat 2D plane, right? We know in a flat 2D plane, this has a total of 180 degrees. But if I take a triangle on the sphere, so let's do a really cool triangle. I'm going to take a line of latitude or longitude, excuse me, coming down to the equator here. It hits the equator at a right angle. And then I'm going to come out at a right angle down here. So this is my North Pole. So I can find two lines of longitude that meet at a right angle up at the North Pole. Why not? And that also down here is a right angle. So look, I have a triangle, a curvy triangle, and it has 270 degrees. Okay, so that's bizarre. That leads into, or is example of elliptic geometry. Okay, that's what you get when you, instead of assuming there's one parallel line, you assume that there are no parallel lines through that point. So you change that parallel postulate to be there are no parallel lines. Okay, if you change the parallel postulate to be there are more than one, so there's more than one parallel line, you get something called hyperbolic geometry, which is really hard to draw. But in it, you get triangles can look like, I don't know, something like that, or like that. Anyway, they have a weird curved in feel. These end up having less than 180 degrees. Okay, and you can kind of see that from the pictures, the way they kind of bend in. That is now called hyperbolic geometry. So here's what's cool. We think in terms of Euclidean geometry, right? The world around us seems to match Euclidean. When you stare at the wall in front of you, you're seeing Euclidean geometry. But hyperbolic geometry, we are now discovering, seems to match with some stuff about the universe as a whole, or things far away from us in the universe and how they move and relate and interact. So that's neat. Elliptic geometry can be sort of used with, you know, the Earth and the surface of the Earth and whatnot, dealing with that. There are other uses, but those are pretty easy to understand. So yeah, so the gist, the takeaway is that just because something is seemingly super obvious, like that if I have a line and a point not on the line, that there's only one parallel line through it, doesn't mean that has to actually be true. We can develop these other geometries by changing that and following our mathematical logical rules. So I hope that was interesting, and that's your Fun Fact Friday.